In this lesson, we'll be exploring limits that involve infinity. Until now, all the limits that we've worked with, both graphically and algebraically, have led us to a defined numeric value, or we found that the limit did not exist. You'll notice that today we have two learning targets, the first of which that we'll be comparing magnitudes of functions to find the limit to infinity. So this is specifically when x is going to infinity, and we'll be looking at these limits algebraically. The following set of rules is only to be used when the limit is approaching infinity or x is approaching infinity. So if x was going to 3 or 0 or some other numeric value, you couldn't use these comparisons that we're about to talk about. And the comparisons are, we're going to be looking at the exponents of both the numerator and denominator in a function that is a quotient. So let's look at the three scenarios. Our job is to compare the exponents of the leading terms, in other words, the terms that have the highest exponents in both the numerator and denominator, and that's going to give us our limit value. And many examples, a couple of which you'll see in this section, you'll have to simplify first algebraically. So our first scenario is when the exponent in the numerator and denominator are actually equal. In that case, what you do to find the limit value is to reduce or simplify the coefficients of the leading terms. So in this example, we see that the exponents a and b are equal. So our coefficients in front of the x terms are c over d. And if we could simplify that, we would. And the reason that we are coming up with that ratio as our final limit value is because we're looking at the rates of the two functions. We're trying to see which function may be increasing larger, faster than the other. And in this scenario, since they are increasing at the same rate, they basically cancel each other out, and you're left with just the coefficients. A second scenario is when the exponent in the numerator is bigger than the exponent in the denominator. That means our top function is increasing at a faster rate. A simpler way to think about that is it's the bigger function over time. If that happens, the function in the numerator actually overtakes the function in the denominator, and basically the function in the denominator goes away. So if the bigger function is on top, your limit value in the end is actually infinity because it gets bigger and bigger and it's unbounded over time. In the opposite scenario, if your exponent in the denominator is bigger than the exponent in the numerator, the function in the denominator, or the bottom, is a bigger function because it's increasing at a faster rate. It will basically cancel out that numerator function as it gets bigger and bigger, and so the final limit value will be 0. Since these three rules are so similar, especially the last two, it might help you to come up with a little shortcut to help you memorize the difference between the three. So off to the right margin, I have same over same. You just take the coefficients. Big over small is infinity. Small over big is 0. And I have heard people say that the big over small, they like to say it's BS because infinity is not a real value. So if that helps anybody, I'm glad I shared it. Let's look at 3 examples. This first example is pretty straightforward. I just wanted to remind you one more time that we are specifically looking for limits as x approaches infinity. So it's really important to not overlook that value before you jump into these 3 rules. But once you have made sure that's going to infinity, we compare the exponents of the leading terms, or the highest exponents, in both the numerator and denominator. I see that it's 2 in the numerator, 3 in the denominator. So that situation is our small over big, and our limit value will be 0. So it's a simple comparison. There's no work to be shown for this one. The second example is not as obvious as the first. I do recognize that x is going to infinity, so I'm going to employ one of these 3 rules. I see right away that the highest exponent in the denominator is squared, or 2, but it is not clear at first what the highest exponent in the numerator is. And I could take the time to multiply all this out, but I'd rather work smarter instead of harder. So I've got to identify what are the 2 terms that I would multiply together to give me the highest power. And that doesn't take too long to figure out that it would be 2x times x, which is 2x squared. And that gives us a same over same scenario. So I would take the numerator coefficient, which is 2, divided by the denominator coefficient 8. So set up that ratio. If you can reduce it, that's great. The final answer will be 1/4. This next example is pretty similar in that we are going to have to do a little algebraic simplification first. And the denominator exponent is pretty obvious that it is going to be squared. But I set this one up a little bit differently so that you would have to take your time, because if you're working too quickly, you might think you just need to distribute the x to this 2x because it's the first term. A lot of people are misled by this word leading term, no pun intended. But you really have to keep your eyes open and make sure that you are identifying which terms would actually give you the higher exponent. In this case, it's the second term that appears in that binomial. So I'm going to multiply that out and then compare my coefficients. I think I just said coefficients when I meant exponents. So when I compared my exponents, I had x to the fourth in the numerator, x squared in the denominator. So that is a big over small scenario. So that would give me a limit value of infinity. So you now have one algebraic example of each of the three scenarios. Now that we've seen a few algebraic examples, let's go ahead and talk about limits involving infinity from a graphical perspective. And when we first started talking about limits in this course, we said that we were looking for a numeric value that represented the behavior of the function. And when we think numeric, we're usually trying to come up with a specific number. But in some cases, and it's actually considered a special case, the limit does not exist, or in other words, it goes to a numeric value that doesn't exist, and that is infinity. So this example is set up like we've seen in the past, where the entire first row looks at a limit as x approaches a specific number. This is 0. We're going to look from the left to the right and then determine if there's an overall limit. So in this graph, even though the graph doesn't present the arrows, what I'm going to do is, as I look from the left and the right towards 0, I went ahead and drew in some arrows to let myself think about the graph or the function extending beyond what we see on the paper. So as my function approaches 0 from the left, I think about that graph going down, and it is going to go down without a limit or bound to negative infinity. And as x approaches 0 from the right, it's going to go up forever and approach positive infinity. Now my overall limit, if these do not match, even though they're both infinities, they're different values of infinity. So we know that that gives us a limit that does not exist. In the next row, we're looking at the function as x approaches 3 from the left, right, and overall. And I went ahead and drew in the arrows for that. It's kind of a funky piecewise, which appears to have a vertical asymptote, but then also has a point on the asymptote, which bugs me. It probably bugs you a little bit too. So as we're approaching 3 from the left, it looks unbounded and goes up forever to positive infinity. And coming in from the right-hand direction, it looks like it approaches a y value on the x-axis, which would be 0. And just as in our last example, since our left doesn't equal right, our overall limit will be does not exist again. Unlike the first two examples, it's not always the case that limits involving infinity have an overall limit of does not exist. So I think this third example is a good illustration of that. If we are looking as x approaches -2 from the left-hand direction, the graph is going up forever, positive infinity. And the same thing happens as x approaches -2 from the right. And so finally, we have a left and right-hand limit that are equal. And even though it's a infinite value, we do have a match. So our overall limit would be infinity. In the last row of this example, we have two more limits to look at, and they're different than any that we've seen so far, in that they are not going to a specific x value, but the function is approaching infinity, or what is the function doing as its x value approaches infinity or goes to the right forever, basically in simpler terms. So if we look at our graph and think about that graph extending to the right forever, it looks like that function is going to continue to increase without bound. I don't see an asymptote or anything that's going to stop it. So we're going to say that the function approaches infinity as x approaches infinity. In our last question, we're asked, what is the graph doing as x approaches negative infinity, or all the way to the left, so if it kept going and going. So if you look at that, it appears to flatten out here on the x-axis. We're not sure that there's an asymptote there, but I think it's pretty safe to say we're approaching a y value of 0. That last example is a good illustration about how infinite limits can help us find asymptotes, and that is our second learning target, which we'll go ahead and tackle in class together.